Hi, everyone. My name is Chris Conlon, like Yoko mentioned. Thanks for joining us today for our medical device security webinar. Our agenda today, we're going to start out with an introduction to wolfSSL, look at the medical device landscape and some of the attacks that have been occurring recently, go over the regulatory landscape, especially for medical devices in the US, some security trends that we've seen, go through a couple of use cases of medical device consumers of wolfSSL, and then some of the solutions that wolfSSL has that can help you secure your medical devices. At the end, we should have some time for questions and answers. So save your questions for then, and we'll be happy to answer them. So in general, wolfSSL secures lots of medical devices in a lot of different types of products. We have patients in all the different areas that you can see here on this slide, which is essentially, all these things are either communicating and need a secure transport channel, or they're using encryption to encrypt data at rest. As a company, wolfSSL was founded in 2004. Right now, we have over 2,000 commercial customers using wolfSSL products, and we estimate that we secure somewhere around 2 billion active connections at any one time on the internet. We focus on really three main areas. So the first area is securing data at rest. This is done with cryptography. The second area is securing data in transit. This is done with SSL and TLS or SSH. Typically, this is over TCP/IP, but could be over really any transport medium. We have people running TLS over things like serial connections and just memory buffers. And then the third area is doing firmware updates. So a combination of securely transferring the firmware update and then securely updating and booting the device. This slide shows you our current product lineup. Our main product is wolfSSL, our SSL and TLS library. Underneath that sits wolfCrypt. That's our cryptography library. We have a couple of validated and certified versions of wolfCrypt available for FIPS 140-2 and 140-3, DO178C for avionics, and also an asynchronous crypto module for use on the server side with accelerator cards like Intel Quick Assist or Cavium Nitrox. We have our own MQTT client library, our own SSH library that supports client and server side, our own TPM library called wolfTPM, which is a TPM 2.0 library. We have a secure bootloader called wolfboot, a secure embedded intrusion detection and prevention system we call wolfSentry. And then we offer commercial support and consulting for curl, the command line utility. We have the author of curl on board as a wolfSSL engineer. And we have a version of curl that's pared down meant for resource constrained devices, which we call tinycurl. Now, all those primary products are written in C. We do have users who want to use us from other languages. So the second row there, you can see are some language wrappers for wolfSSL for Java, C#, Python, and JavaScript. So if we look at the medical device landscape, as of 2019, there were 15 million medical devices in US hospitals. So that averages out to about 10 to 15 connected devices per patient bed. And if you look at this survey that we found from Palo Alto Networks Unit 42, it gives you kind of an idea for what the landscape looks like. 51% of threats for healthcare organizations involve imaging devices, and 83% of the imaging devices are running an unsupported or older operating system. So you can imagine those older unsupported OSs likely have vulnerabilities in them by now. 72% of the healthcare VLANs mix IoT and IT assets. And so this can make it easier for attackers to find their way into a network, maybe using an attack vector that you might not be thinking of. And 98% of all IoT device traffic is still unencrypted. And so that leaves a lot of room for improvement in switching over to an encrypted communication channel. We've seen more and more attacks showing up on medical devices. According to the Healthcare Breach Report from 2021, medical device attacks increased by 55% in 2020. And we've seen some more vulnerabilities both being discovered and more being publicly disclosed. A couple of the recent ones were Urgent 11, which was a set of 11 VxWorks TCP/IP stack vulnerabilities. And there was also the Swaney tooth, which is a Bluetooth BLE vulnerability. Another common thing we're seeing is ransomware attacks are becoming more prevalent. A couple examples, the WannaCry ransomware, which happened, a number of years back, but that affected hospitals all around the world. And in 2020, another example, a German hospital was attacked and resulted in delayed patient care. Some of the patients had to be diverted over to another hospital. So all of these are things that we're trying to prevent against by, starting with producing more secure medical devices from the beginning. If you look at the old, traditional medical devices, they were simple and unconnected. So, they really didn't need a lot of layers of security other than physical security. But now the current medical devices, everything is networked. There's lots of different layers of software and hardware components interacting with each other. There's a need to protect patient medical data that's now being transferred around and stored in various places. New attack vectors for things like implants that people really didn't have to think of before, but which could be life-threatening if an implant is hacked and malfunctions. And a lot of these devices now are updatable, so you don't want malicious firmware being flashed down to a medical device. So if we look at the regulatory landscape, this will be more specific to the US, which is where we're seeing a lot of the medical devices, at least being over here in the US. The FDA has a Digital Center of Health Excellence, and they put out some guidance. This guidance is a draft guidance from April of 2022, and we'll be referencing this as we go along in this presentation. The first thing to call out here is that we're seeing a lot of demand for FIPS 140-2, and upcoming will be FIPS 140-3. This really is a best practice for use with HIPAA security rules. And if you're selling into any kind of Department of Defense or government project, particularly in the US, this is going to be a requirement. FIPS is really oftentimes a checkbox item for these kind of consumers selling into these areas. And some vendors try to use loose terms like designated for FIPS or FIPS ready. We find that typically these aren't an official validation and won't pass an audit if that customer ends up going through one. The current FDI guidance does include some wording on cryptography. It does recommend that you use industry standard algorithms and protocols. It also suggests that you use current NIST recommended standards for cryptography. And this is where FIPS would come into play with FIPS 140-2 and NIST Suite B. So next, we'd like to share some of the use cases and trends that we're seeing from our customers here at wolfSSL. If you're in the medical space, some of these might look familiar. And if not, it'll give you an idea for what some of our medical device customers are running as far as platforms and technologies. So this first use case is an endoscopic surgery device. The wolfSSL products that this customer used were Wolf TPM and Wolf Crypt. This was on a Xilinx UltraScale Plus with QNX, and they were using the TPM 2.0 module for secure key storage on the device. This customer did have some challenges processing high volumes of streaming data, but we were able to use Wolf Crypt and tune that to meet their performance requirements. The second use case here is a dialysis machine. Here the products used were Wolf Crypt, Wolf SSH, and Wolf SSL. This was on an NXP IMX6 device using the CAM hardware accelerator. This was on Green Hill's Integrity RTOS. And here the biggest challenge that we saw engineering-wise was getting wolfSSL integrated with the CAM device on Integrity. We had to write kind of a custom driver there, but that did turn out successful, and we were able to provide the customer with a working solution. A lot of times it can be interesting to look at the performance comparison of software cryptography versus hardware cryptography. And so we have a web page on our website, which is linked here, which has a lot of our reference benchmarks. These little diagrams and charts here that you can see are software versus hardware cryptography using the IMX6 CAM module. The next use case we have is a portable defibrillator and ventilator. wolfSSL products used here were wolfcrypt FIPS, wolfSSL, and also our Python wrapper for wolfSSL. This was again on an NXP device, this time an IMX7 running Yocto Linux. Some of the open source ports that were used with wolfSSL here were Nginx, Python's URLib3, and Python's WebSocket client. And this customer needed a FIPS 140-2 validated crypto module to put into their next generation device, which was going to be sold into the VA. Next use case here is an embedded and connected insulin pump. This product used wolfSSL on an STM32 with ThreadX. And this customer needed a well-supported library that also had a small footprint size. And so we optimized wolfSSL to correctly fit down into their footprint requirements and help meet their end goals. The next use case here is a connected device hub. And so this was using wolfcrypt FIPS along with wolfSSL on an NXP IMX7. This customer also needed FIPS validated cryptography, and they were using this to add authentication to their device hub, specifically using TLS 1.3. This use case is a migraine helmet. So this just used wolfcrypt just for cryptography operations. There were two different platforms here from NXP, an M4 based platform running free RTOS, and an M0 just running bare metal with no operating system. This was a helmet that was designed to help cure migraines, and they needed wolfcrypt in there to help secure the Bluetooth communication from the helmet back to a tablet or a backend server. And then I believe this is the last use case we'll cover. This is a tablet used during organ transplants. This used wolfcrypt on an NXP IMX8, again using the CAM for hardware acceleration for cryptography. And this was on the QNX RTOS. Our engineering effort here focused on optimizing AES and ECC performance. We also did need to put in some effort to get the CAM working right on QNX. This is generally a tablet used to monitor other devices, and wolfcrypt is used to secure data in transit and data at rest. So some of the trends that we've seen with medical device customers are that they want to secure data in transit using TLS with modern protocols. And so using TLS 1.3 is the latest version of TLS available today. They're looking at securing data at rest by using encryption. We see a lot of customers who want to use secure enclaves or secure key stores, which could include a TPM 2.0 module for just layering on an extra layer of security there for key storage. We see people wanting to leverage hardware-based cryptography. This gives them accelerated performance. Typically, we'll see at least 5 to 10 times performance on embedded platforms. And then we also see people wanting to support secure firmware updates and secure boot. This adds in the ability to patch vulnerable software and also extend the lifetime of your device. So next up, we're going to go over a few details of wolfSSL. This is our SSL and TLS library. So wolfSSL supports up to TLS 1.3 and DTLS 1.3. DTLS 1.3 is very new. We just released it as of 1 or 2 versions of wolfSSL ago. wolfSSL's footprint size is 20 to 100 kilobytes typically. This depends on your compiler and the optimization level you're using. RAM and runtime memory is 1 to 36 kilobytes per session. And wolfSSL is very portable. We support 30 to 40 operating systems now. So that's everything from bare metal through a number of RTOSes, all the way up to your standard Windows, Linux, Mac. We have an OpenSSL compatibility layer. This makes it easier to move an application that had been using OpenSSL over to wolfSSL. It includes a couple thousand of the most commonly used OpenSSL functions, and it gives you the same API prototype, and then just maps down to wolfSSL logic internally. We've integrated wolfSSL to a number of different web servers, including Apache, Nginx, Lydie, and Mongoose. added support for a large number of hardware cryptography platforms. We have FIPS 140-2 validations available for wolfCrypt, and 140-3 is currently in progress. And then we've ported wolfSSL into a lot of open source packages. And so if you have a need to use wolfSSL with things like Python, OpenSSH, WPA supplicant, that's something that we have patches available or submitted upstream to the project proper. So, one of the big things, at least for us in the US here, is the requirement for FIPS validated cryptography to help meet regulatory requirements. So the next couple slides, we're just going to cover a little bit more about FIPS. And so FIPS is a validation that in our case is around our cryptography module or library. We've drawn the FIPS boundary around a subset of wolfCrypt. And so the wolfSSL TLS code is out of scope of the validation. And that's done on purpose because most of our bugs and vulnerabilities are found at the SSL and TLS level. And this allows our customers to use the same validated version of wolfCrypt and still be able to update to newer versions of wolfSSL. We have a FIPS 140-2 certificate available today, which is certificate number 3389. You can look that up on the NIST website and see the details of that there. We do have a FIPS 140-3 certificate on the NIST's in process list. And so we're expecting that to come out sometime this year. There are a couple special things that happen at the code level when you're using a FIPS validated library versus just a normal wolfCrypt library. One of them is a power on integrity check. This does an HMAC SHA-256 over the object files within the wolfCrypt FIPS boundary. And that happens at runtime to make sure that those files haven't changed between compile time and runtime. The second item that's different here is a set of known answer tests. So these are essentially algorithm test vectors for each algorithm inside the FIPS boundary. And these are run again before the application is allowed access into the library. So just a diagram of those things running. If they both pass, the application is allowed access in to use the crypto module. If they don't, then the library enters an error state. So for validation options, the most common thing we see people do is add a new operating environment, or OE, to our existing FIPS certificate. And an operating environment is a combination of an operating system and version, the processor that wolfCrypt is being run on, the platform, and then the version of wolfCrypt itself. We can also do rebranding validations where we rebrand our certificate in a company's name. That can be useful for marketing reasons primarily. And then we can either grow or shrink the module boundary if needed. The time frame for all these things is really dependent on the scope of operating environments and what that operating environment looks like. If that's an embedded one that we haven't done before, or if that's more of a desktop type platform or one that we've done in the past. It also depends on our lab and the CMVP wait time at NIST. So the next thing, that's really important for our medical customers is secure firmware updates. This allows you to update your device in the field. In general, all software contains bugs and vulnerabilities, like most of you know. And, in general, firmware updates are important to be able to update your software to minimize your vulnerability attack surface. You can update and rotate keys and certificates. You might need to do that if, a certificate is getting close to expiring and you want to push down an updated cert to the device. And this can also help extend the lifetime of the device in the field by either, patching vulnerabilities or extending the functionality of your device feature-wise. And so firmware updates are important, but secure firmware updates are even more important, especially so in life-critical applications and devices. That FDA guidance document that we looked at earlier in the presentation does have some wording around this. It states that devices should be capable of being updated in a secure and timely manner. And so wolfSSL helps our customers meet this goal with wolfBoot, which is our secure bootloader product. wolfBoot is a very lightweight, portable bootloader solution. It uses safe coding practices, which means no dynamic memory use. It works on a dual bank update design. And so you have the primary partition where your firmware image is living. That's your main application. You have an update partition where you place the updated image. And then there's a swap section that's used during the update. wolfboot is interruptible and power fail safe. So if you lose power during the update process, it'll safely roll back to the previous image. It has some protections against downgrade attacks. And in general, it's pretty easy for us to port to new platforms. We have a number of already supported platforms and can pretty easily add new ones if your platform isn't on our supported list yet. Another thing that we think is kind of interesting as it applies to medical devices is intrusion detection. And so if you remember that earlier stat that we saw, that 72% of healthcare VLANs mixed IoT and IT assets, that means you could potentially have malicious actors on the same network as your device, and having a way to detect a malicious activity or an intrusion and then take some kind of action on that can be very helpful. Benefits to intrusion detection and prevention on a medical device could be to detect malicious activity. You can use either static or dynamic rules. You can receive events of that malicious activity, and then you can take some kind of action based on that. You might want to log that. You might want to send an alert, or you might want to actually just shut down the device or the connection. And so to help our customers reach this goal, we have wolfSentry. This is our lightweight IDPS solution. It's a universal dynamic embeddable IDPS. We essentially wanted to bring kind of desktop and server class concepts of a firewall and IDPS down to an embedded system. And so it does have a firewall support that can either use dynamic or static rules. It has user-defined events. And so you can control what happens, when you detect an event happening. You could, just log that in a simple case to a log file, or you could do something more complex. We do have kind of tight, nice integration with our existing products. So if you want to use wolfSSL, wolfMQTT, or wolfSSH with wolfSentry, we just have simple build options that allow you to link them together. And then, we have great products, but one of the things that make them great and helps us sleep better at night is our testing. And so we try to put a lot of effort into testing to try to fix bugs early and minimize vulnerabilities that make it into our end products. So we don't like crashes to happen, in any software using wolfSSL. And this can be even more fatal in medical devices where some of those are life critical. We do all kinds of testing at wolfSSL. Some of those you can see here on this slide. Everything from API unit testing to cipher suite testing and algorithm testing. We do benchmark testing to make sure we don't slow down the library. Do static analysis with Coverity, ScanBuild, and Facebook's Infer. We do memory error detection using Valgrind and Clang's fsanitize address. Do interop testing with pretty much all the other major TLS implementations out there today. We do real world builds. So this means that we build our customers' build configurations on a nightly basis. Compiler testing with a number of different compilers, both desktop and embedded. Every single line of code that makes it into our products is peer reviewed. And we facilitate that through GitHub and pull requests. We also work with third parties to do testing on wolfSSL, whether that be auditing, pen testing, or fuzz testing. We do our own fuzz testing with over 6 different fuzz testers now. And then we kind of wrap all this up into a continuous integration cycle using Jenkins. This is our rainbow of testing. It essentially shows you, more types of testing that we do. And as I said, we're always adding to this. This diagram just kind of gives you a glimpse into part of our software development process. So you can see that all these things are leading to source code in the center. Up in the top, we have some of the NIST, FIPS, guidance. We have some of the IETF, RFCs. And so those make it into software specifications and design, down into design documents, which we base our implementation on. Also writing our API documentation off that. Over on the right side, we have the CAVP and CMVP. Those are validation processes we go through for FIPS validation. We have API consistency tests, unit tests, interop tests. These are all things that you saw in that previous slide we looked at. And then down below, we have some more test tools we use. So static code analysis, memory checking, and fuzz testing. So in summary, why use wolfSSL for medical device security? You can leverage our expertise and industry experience. We've worked with a lot of customers in this space, so it's likely that we've seen a product, similar to yours or with some of the same challenges. We do offer commercial support and assistance. So if you run into problems, either getting up and running or in the field with wolfSSL, we can help you solve those and get past those quickly. We offer integration assistance, so we can help you get wolfSSL products up and running in your environment. We have a wide breadth of platform, operating system, and compiler support, supporting 30 to 40 operating systems. We do a good job of optimizing for low memory use and small footprint sizes. So this can help us fit down onto your more resource-constrained devices and also leave you with more memory space for your application. We have modern protocol support with TLS 1.3 and DTLS 1.3, have our FIPS validated cryptography modules. We offer our hardware cryptography integration support for performance, secure element support, and TPM 2.0. We think we're the best tested cryptography and TLS implementation available today on the market. We have our full product suite available, and so all of our products work very well together with each other. And then we've integrated wolfSSL with a lot of open source packages. So if you have a need for using FIPS cryptography with Wi-Fi authentication with WPA supplicant, that's something we can definitely help out with. So thanks for listening to my slides so far. If you have any other questions generally, I'll be happy to answer them now. If you would prefer to contact us offline, you can email our Japan team at info@wolfssl.jp or visit our website at www.wolfssl.jp. You can also find all of our code on GitHub if you'd prefer to take a look over the code base or pull it down and try it out yourself. We're just at github.com/wolfSSL. So thanks again, and yeah, I'll open it up for questions. Feel free to use the Q&A feature of Zoom to ask questions, and I'll go ahead and read them off there.